This is a very important idea in physics. Maybe no more important than F equals ma, but it is F equals ma in a different form. We've recast physics to be in terms of energy and work. So here's a flat surface, and for the beginning, I'm going to let friction oppose the pulling force, and I'm going to pull the box horizontally a certain distance d. So we're going to move the box from here to here through the distance d. We know that the net force is ma, that's Newton's second law, and the net force are the sum of the forces acting on the box in the direction of motion. That's why this force does not directly appear in the equation, because this force is the normal or perpendicular force. It creates the friction force. So F pull minus the friction force is ma. Let's multiply through by d, because what is force times distance? We talked about it. Force in the direction of motion times the distance is work. So F pull times d, that's us doing work. Work done on the box by us is MAD, which we know is 1/2 mv squared, the change in kinetic energy from 0 to v, plus, because we're moving this to the other side of the equation, so the minus becomes a plus, work done by the box, which is always friction. The work done by an object will always be friction on the SSAT. So the work done on the box is the change in the kinetic energy, because I'm on a flat surface. There's no change in height, so there's no gravity potential energy to worry about. But this is, this is the basic entry level work energy theorem, that the work that we do on a box first has to overcome the friction, and whatever extra work we put in after we overcome the friction, we can use to change the energy of the box. So we must overcome this guy, friction, to get energy. Now, we need to take this into 2 dimensions, because the work energy theorem has to account for potential energy too. But the work done on the box is change in energy plus work done by the box. And when we go to the inclined plane, which we know how to draw, we've done a video on that, and we pull the box up a certain distance, which creates a certain height difference, we have a normal force created by gravity that's perpendicular to the surface. It's mg cosine theta. That creates the force of friction. So we can write the net force. It's the sum of all the forces in the direction of motion. It's F pull in this direction minus the force of friction minus the gravity force created because there's a tilt. That's mg sine theta. So we have this as our Newton's second law equation, which easily turns into the work energy theorem by multiplying through by the distance d, because force times distance is work, and work is energy. There will be a question on your test, and it's going to ask you in the following 5 things to find the scalar, the non-vector quantity. Work and energy are scalars. When they say find the one that is not a vector, look for work and energy. If you don't see it, look for time. Time is not a vector, even though it travels in one direction only. So work and energy are scalars. And when we multiply through by d, we get MAD, which we recognize as 1/2 mv squared. I derived it for you in an earlier video, that the kinetic energy is equal to the work that we do on the box, F pull times distance, minus the friction work, force of friction times distance, minus the work done by gravity. And remember, the sine of theta, the sine of this angle in here, or the sine of this angle in here, is going to be this guy over this guy. So it's going to be h over d, height over distance. That's the sine of theta. When I plug that in, the distances will cancel, and I'll get mgh. Recognize mgh is the work I do in lifting something. So the work done on the box, that's this guy here, is going to be the change in kinetic energy. Bring this guy over, it becomes plus. The change in potential energy. Bring this to the other side, the minus becomes a plus. The work done by the box, which is always friction work. So here is the work energy theorem, another way of doing big four problems without using the big four. That the work done on the box is the change in energy plus the work done by the box. We never bookkeep the work done by gravity separately. It's contained right here in the change in potential energy. A lot of students try to introduce a work of gravity term. It's already there. Don't get fooled and double bookkeep it. Bookkeeping is a fascinating word. It is the only word in the English language that has this. What does bookkeeping have that no other word in the English language does? I'm going to answer it in the next video as we continue to understand our physics. Suppose we do no work. We don't push or pull on the box. And suppose there's no friction. The work we do on the box is zero. The work done by the box, which is friction, is zero. We don't pull. There's no friction. The change in energy is zero. This is conservation of energy. And as I said, please remember, gravity work is part of the change in potential energy. So we don't have to bookkeep it separately. So I'm going to do an example and talk about these in some problems because it's important to see how this is used. And also think about that word bookkeeping. It's very special. Someone once asked me on my radio show, Stump the Professor, what's the only word in the English language that has blah, 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 blah. And I didn't know. And I only found it when I was writing it one day. So maybe if you write out the word bookkeeping, you'll see what's special about it.